are now recording. Let's get the slideshow set up. All right. First, I want to know, any questions for anything we've done so far? Not? Okay, I'm trying to recall. I know we didn't quite finish chapter 6 last time, and I think I asked you if you wanted the test before the weekend or not. Did any of you bite on that? No, I didn't think so. Okay. So I know we'll finish chapter 6 today. We're in 6.5, and then I'll give you your test on chapter 5 and 6. I just can't remember. I think I was going to go run it off if you wanted it, but you didn't want it, so I didn't go run it off, and then I don't feel like I run off. So I took down things this morning, but I forgot this class did not take that, so I'll have to go get that for you in just a couple minutes. So it'll be a good maybe break time. Okay. Now I think, had finished this problem and that problem. No. Well, let's see. No. This is the problem we were starting on. We finished that one. Yeah. So this is example 3. So any questions before we get started on example 3? All right, example 3 is one of these classic kind of problems that calculus books love. Pumping water out of a tank, okay? Here we have a spherical tank of radius 5 meters. Now, I don't draw spheres too well. In fact, I don't draw anything too well. Okay, let's just imagine this is a sphere. Okay, something like that. I think the next page is going to have a much better picture of than mine. So why don't we just go to that page? Okay, we'll come back to this if we need it. There's a picture. Okay. Here we have, I'll zoom in just to begin with, and then we'll zoom out to do our writing. Okay. A spherical tank of radius 5 meters. Okay. Now, have y'all ever seen a spherical tank before? Ever headed south on 65? Going past Clanton, Alabama. The Big Peach, exactly. Yeah, that's basically a sphere with a little thing to make it look like a peach. But that's a spherical tank. Not that it matters any, but you have seen a spherical tank before. I'm guessing radius 5 meters. That would be about like, that's probably not too far from what that is. That may be this may be a little bit larger than that because, by the way, that would be a diameter of 10 meters, and this room is about 3 meters high, so a 3-story building would be about 10 meters, okay? I don't think it's quite that big, but you get a general idea, okay? It may be. It sits up there, so maybe it is bigger than I think. Spherical tank of radius 5 meters is filled with water. Calculate the work W, that's what we're looking for, performed against gravity in pumping out the water through a spout at the height of 1 meter at the top. At a spout of height 1 meter at the top. The density of water is 1,000 kilograms per cubic meter. Okay. So what we're going to do, similar to what we did on the last one, is imagine dividing this sphere into horizontal slices. Okay? And here's Chris. Horizontal slices here. Okay? And the thickness of each slice we're going to call dy. Why not? I mean, it's this way. So that would be, for instance, y sub I minus y sub I minus 1. That would be the ith slice. Okay. Okay? So we slice it this way, and we're ultimately going to let that coalesce to a dy. Delta y is y sub I minus y sub I minus 1. Okay, now, the water exits from a hole at the top, so you're pumping the water out. I think I would have rather had a spigot down here and just turn it on, but no, we're pumping it out. That makes more sense, I guess. Let's say maybe this is underground and we're pumping it that way. Okay, so our water is exiting the hole at the top. Okay, now every slice of water is going to have about the same elevation. We'll just call that our y sub I. Okay, and it's interesting how they did this. They didn't have to do it this way, but they chose y sub 0 to be sort of the equator of that sphere, the great circle at the center, and then have a y going from y sub 0 where that's minus r, which in our case is 5, and going to plus 5. Okay? Now, is there any specific reason for doing that? Probably, because then you can form your equations from the center of the sphere, and that's a lot easier than forming one from some other place in the sphere. So we're going to do that. So that's a good, convenient place to have your y0. Okay? Now, what you've got to get is the volume of that slice. Okay? Because you've got the density of water, 1,000 kilograms per cubic meter. Okay? So if we had the volume of the slice, then multiply that by the density, and that gives you the mass of the slice. The mass of the slice, that's what you're pumping up, the mass, mg, that's your, they don't have that on the thing yet, but that's the work is the force is mg, okay, and the so we're going from there. You're working against gravity, so mg y is going to be how much work you're doing. So you need the mass, so that's why they put the y0 here, so that makes it really convenient to do that. So now, so like we said, we want the mass of this slice here. This is your delta y, okay? The area of this slice, you might call, would be pi little r squared, where little r is the radius of the y depth, okay? Okay? And that little r, and this is why you needed the center of the circle in here, Pythagorean theorem tells you, you're wanting everything in terms of y because that's going to be your dy. So your depth here, now this isn't quite the depth, okay, but y is measured from the center to up here. We'll get on how far you're pumping later, okay. So if this is your y, how far above or below, because y could be negative or positive, you are from the center. They've chosen this one to be up here. Then this is your capital R, which in our case is 5 meters. Okay, they told us that. This radius here, by Pythagorean theorem, will be the square root of r squared minus y squared. Okay, so that's where they get that radius there. Now, the volume of this would then be pi little r squared. Well, when you square this, you lose the square root. So it's going to be pi times this times your delta y. That's your volume of water. Does that make sense? Okay. Multiply that by the density. You've got the mass of the water. Okay. Now, that mass of water that's in this blue band here, you're pumping that a certain height. Now, how high are you pumping it? Your hole is up here, so you're having to pump from here to there. Well, this is y. This is capital R, 5. So 5 minus y would be how far you're pumping this layer of water. Okay? You're pumping that r minus y units up. And you see your math works out for you fine, because when you're up here, that's r minus y, that's a number less than 5. But when you're down here, you do a r minus y, but y is a negative number here, so it's 5 plus whatever your y is. So your math takes care of that, so that enables you to start here and not have any problems there. Okay? So I think we've got the basics that we need here. Any questions about it so far? Okay? So let's write down what we just determined. Okay? First we'll do, let me make sure, yeah. The volume of this slice, which I'm going to call a dV because that's just one little portion of that, is going to be the area of that, which is pi times little r squared, but little r being the square root of 25 minus y squared. When you square that, that'll be pi times 25 minus y squared. Okay, that's your area times your thickness, delta y. So that's your volumetric incremental volume. Is pi times this r squared, which just gives you 25, because they told you the capital R was 5, 25 minus y squared times your delta y, the thickness of that slice. So your delta M is going to be this times your volume. So your volume is 1,000, I just hurt my elbow, 1,000 pi times 25 minus y squared delta y. Okay? So that's your incremental mass. That incremental mass you're having to lift. All right. Here's Khalil. Good deal. Okay? That incremental mass, you're having to lift a distance, and that distance we got was your 5 minus y. That's the vertical distance you're having to lift this mass of water to get it to that hole. Work you're doing against gravity. So that's your r minus y times this. So that's your height. So let me back up one. The force due to gravity is the force, the delta F then, is equal to delta M times G, which is, okay. G is 9.8 times this, so that'd be 9,800 pi times 25 minus y squared delta y. So that's your incremental force to get that incremental slice of water up to the top. And then multiply that by the distance, which is your r minus y. So the work, the incremental work would be 9,800 pi, times 25 minus y squared times that height, 5 minus y, times your delta y. I think we got it all in there. Okay? Now I think it's probably a good idea to go and multiply these parts out. So that would be 9,800 pi times 125 minus 25y, these two, those two, minus 5y squared plus y cubed. Okay, then times your delta y. All right. Think we're ready to integrate, right? The total work would then be 9,800 pi. Those are all constants. Pull them on the outside. The integral. Now, where are you going from and to? They didn't tell you. Did they say the tank was full? Spherical is filled with water. It's full. Okay. So you're going to pump the water out of that. So you're going from y equal r 5 to y is equal to minus 5 meters. Okay. Rather odd to be doing it that way, but that's how we set it up. So we'll do it that way. It's y is going from 5 to minus 5 meters. Okay, I could put the m's in there, but I haven't put the other units. And then it's merely this, 125. This is such a pain in the neck. Okay, 125 minus 25y. The writing is so slow. Minus 5y squared plus y cubed, and the delta y becomes a dy. Okay. Now, it seems to be a bit bizarre to do it that way. If you like having the plus 5 on top and minus 5 on the bottom, that just negates everything here. So that would be a minus plus plus minus. But let's just do it. Let's see. Wait a minute. Oh, I'm sorry. Missed something. Work performed in pumping out the water through a spout of height 1 meter at the top. So they didn't have it in their picture. Did they? No. Okay. The height here is here, but you've got a spout that's another 1 meter tall. So that's going to oh boy, that makes this a 6 minus y. Okay, because you're pumping from 1 meter above the top. So that messes everything up here. So let's change this. 6 times 25 is 150, I believe, isn't it? Oh, that one could have stayed the same. This one changed. Okay. Well, I needed to erase more than that. 150 minus 25 minus 6. So I needed to change this. Okay, the eraser is very slow. Okay. 150 minus 25 minus 6 y squared. Okay. I think I got it now. Now, that's what we're integrating. And they didn't do they did the minus on bottom, plus on top, but they didn't change their signs, and here's why. What's to say you're not pumping this layer first and then that and that and that and that? It works out the same, so therefore they if you had wound up with negative work, you know you had the sign wrong and just change the sign. But this one, we're going to do it the normal way. The plus, the smaller number at the bottom and the larger number at the top. That was all the work, literally, in the problem. The rest is, the calculus is easy. It's 9,800 pi. And what's the antiderivative of that integrand? You tell me. Help me. Entire root of 150. 150y, I hope is what I heard you say, right? Okay. Minus 25 over 2y squared. Heard you say that too, right? Okay. Next. Minus 2y cubed. Very good. I don't have much room, but help me here. Plus y to the fourth over 4. Evaluate that from minus 5 to 5. Now, do you think you have any symmetry here that's going to help you out? The answer is no. Okay, there's nothing you can do to change this around. If this were an even or odd function, then you can think about it, but this is a neither function, so there's not going to be any way that's going to help. So that's going to be your 9800 pi, okay, times, and let's do the plus 5 first, and that's going to be 750. Am I doing that right? I think that's right. 150 times 5. I think it's 750, isn't it? Okay, 750 minus, okay, 25 times 25 is 625 over 2. Again, I'm doing it in my head, so I hope I'm right. Minus, and when you plug in y 5 cubed is 125 times 2 is 250, I believe. Am I right? And then we have 5 to the fourth, which I think is again a 625 over 4. Okay? But when you put in a minus, now the minus because you're subtracting the bottom part, and then you have a 150 times minus 5, that would be another minus 750, so that becomes a plus 750. Okay. I hope I'm doing this right. And then a minus times a minus will be a plus, but you have 25 halves times 25, so that's 625 halves. Which I think is going to completely wipe that one out. You have to be really careful of your signs here, but I think that works correctly, because your minus 5 squared is a positive 25, but you had a minus, which is plus, so I think that does wipe that one out. Okay, then you have a minus times a minus, which is a plus, but then negative 5 cubed is minus 125 times, so that would be another minus 250. Okay, because those are a minus times a minus times a minus is a minus. Okay, and then you have a minus again, and this is your 625 over 4. And that's the minus because it's the lower limit, but everything else is plus. So you wipe out your fractions. Oh, that breaks my heart. Okay, that I've lost the fractional forms. Okay, so what do we have now? Well, 750 minus 250 is 500, plus 500 would be 1,000. So this looks like 9,800,000 pi. 9.8 million pi joules. Okay, it's a lot of joules, and that is what they got in the text. Does that make sense? See all the pieces there. The part that I find the most hazardous is down here when you have this part as is, with that plugged in. Then you have a minus this part with that plugged in. So you have a minus here, but you have a minus there, and you have minuses in there too, and you have to keep your signs in order. That's the place where I most typically make errors, okay, is how many minuses are that in a row now, and what does that turn out being? All right, good deal. Any questions on that? All right. They have another little blurb here that was not part of the original problem, but they just sort of threw it in here. A liter of gasoline has an energy content of approximately 3.4 times 10 to the 7th joules. Hence, the work required to pump the water out of the spout is equal to the energy content of roughly 9/10 of a liter, which is pretty close to a quart of gasoline, which that much water, I was surprised to see it, that little gas would be required to pump it. They do have a summary here, well worth your looking, and for some reason they like to introduce this new function L of y. I really don't see how it's helpful, okay, except it gets all your y's together, but just hang on to them, keep up with them, and they're still together. And that's what you got to integrate anyway, so the L of y you have to get back to a polynomial or whatever you've got in y. So I don't see a huge advantage in doing it, but the book loves to do it that way. Work is the integral of L of y dy, which is exactly what we did, but the L of y doesn't help you any. You have to plug in what that is. Okay. Now, y'all like to do preliminary questions or not? Okay, let's do them. Why is integration needed to compute the work performed in stretching a spring? Why is integration required? Why don't you just do a multiplication? Yes, the force is not constant. It's a variable force depending on how far you've stretched it. So you have incremental changes in force as you go, so you have to integrate. Very good. Let's see how they phrased it in the back, but that's the right answer. How did they phrase it? 6.5. Because the required force is not constant through the stretching process. Exactly, variable force. Okay. Number 2. Why is integration needed to compute the work performed in pumping water out of a tank, but not to compute the work performed in lifting up the tank? Okay, yeah, just like we said before, it's a variable force because you have less force to pump it out from here than you do here, than here, 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 more force down here. So again, it's a variable force. But to lift the tank, it's just force times displacement. Okay, very good. That's almost the same answer as before, except the force involved in lifting the tank is the weight of the tank, which is constant, and they didn't say to pump it out is the variable. Okay. Good deal. Number 3. Which of the following represents the work required to stretch a spring with spring constant K a distance x beyond its equilibrium position? I'm going to clear this. Does anyone need this any longer? My scribble. Okay. So let's do this. Which of the following represents the work required to stretch a spring with spring constant K a distance x beyond its equilibrium position? Here are the choices. Kx minus Kx 1/2 mk squared (1/2 kx squared) or 1/2 mx squared. Which of those The following represents the work required to stretch a spring with spring constant K a distance x beyond its equilibrium position. Kx? Yay or nay? That's a force. Because if you think about it, the spring constant is newtons per meter times meter. That's going to give you newtons, which is a force. Now that's dimensional analysis. That's still it. That's Hooke's law, basically, is forces equal minus kx. So those are both forces that are not work. Okay? What in the world is 1/2 mk squared? Let's assume the m is your mass of whatever is at the end of the spring, and k is a spring constant. That's just a constant. That's not a work done. I mean, it would be, x isn't even in there, so it can't be that. How about the next one? Second. That's it. That's it. Exactly. Because 1/2 has no dimension. This is newtons per meter times meter squared. So one of the meters goes out, and you got newton meter, which is the right unit for work. Now that's dimensional analysis, but it's the integration of this thing, or that thing, either one. It's the integration of that, and when you integrate that, you get the k's on the outside, and 1/2 x squared would be the integral of that. That's it exactly. That is a perversion of the kinetic energy equation, which would be 1/2 mv squared. M has nothing to do with your spring constant because M never showed up there. So yeah, you're right. The fourth one is it. And I'm pretty sure they got it right in the back of the book, but let's just make sure they did. Yes, they did. Good for them. Number 4. What does it mean when the integral used to calculate the work gives a negative answer? Okay, that's you're very good in relating energy and work being the same. It actually was a spontaneous event. You opened the valve and the water ran in, or something like that. You didn't have to do any work. Or you messed up science pretty badly. No, I'm sorry, that wouldn't be the case with it. Okay. All right. Let's see how they phrase it. When the force applied is in the opposite direction to the motion. Okay, yeah, I guess that's the same guy. What's that again?
The braking force in cars.
Right.
Be negative work.
Right, exactly. Because it's in the opposite direction. Okay, homework exercises here. Do number 1. Okay, pretty straightforward, simple problem. Then do either 3 or 5 or both. Then do either 7 or 9 or both. Either 11 or 13 or both. Do 15. It's the only one sort of like that. It's a pretty neat exercise anyway. Any of the odds 17 to 21. And then wrapping them up, well, not quite. Any of the odds 23 through 33. And again, I'd probably do more than one of those. Okay. And then either 35 or 37. Now, if that isn't enough for you, you can look at some of the further insights and challenges. I don't require those. I don't require the others either, but if you want to do them, you certainly can. The odds are in the back. And that does finish the chapter. So other things you can do if you wanted to is look at odds, because they have the chapter review exercises in the back too. I'm pretty sure they have odd numbers for those as well. Let me make sure. Some books do things a little differently, but I think this one is odds. Yeah, only the odds. So you can do, if you wanted some extra practice, number 1, any of the odds 3 through 11. Any of the odds 15 through 17, or either 15 or 7. No, sorry. Any of the odds 13 through 17. any of the odds 19 to 23, either 25 or 27 or both, any of the odds 29 to 39, either 41 or 43 or both, and any of the odds 45 through 51, and then I would do 53. Okay, now that leads me to whether, I can't remember if she ran off the test or not. It was last week sometime, and I had carried some stuff down there and nobody was in, and I thought I would come back to it. Okay. Here we go. Wow. Okay. I seem to have multiple copies. Make sure they're the same tests. Okay, there's one. No, they're not the same. No, they're the same. Okay. Okay. All right. Wait, I think I just messed it up. Sorry about this. Okay. Got to get my original separated from these. Okay. Nope. Okay. I do have more than one test. This is the one we're doing. Okay. Got one. Only got one. I have 3 tests. Why do I have 3? I mean, okay. I think I'm going to go with this one. Looks like it's covering the right material. All right. So I've got one runoff, and I need 8 more. Okay. All right. Does anyone have to leave early today? You do. Okay. Let me give you the one that is run off already. Oh, I buried it again. Sorry. Hang on to that. Okay. Since you have to leave early, I'm going to give this one to you. And the rest of you, if you'll catch me 5 minutes before the end, stop me, and then I will run down here with other copies. Sorry I didn't have to make it already. Again, I can't remember if I told you, or the first class, because I missed Monday and Tuesday of last week. Not only did we miss class, which I hated, but I missed some other things that they came out and said, we need this by then, and I was out then, so I didn't have any time on Wednesday to do anything because I have 4 classes, four 4-hour classes, 2 of them with labs, so I'm here from 8 to 9, 8 in the morning, 9 in the evening with no more than a 20-minute break anywhere. So I had no time at all to do anything on Wednesday, so I had to do everything, get all that administrative stuff done on Thursday, and I did not have time to do any copies made or anything else. And I forgot today when I was in my office I hadn't made copies of this. I was thinking I'd already given you the thing, but then I remembered on the way to class, no, y'all said you didn't want them. Yeah, okay. So, enough of my sad story. Let's throw these away and go to chapter 7. It takes a while for it to do anything. All right, chapter 7. Now, not meaning to bias you or anything, but frankly to me, substitution, which we did in chapter 5, everything we did in 6, and this part of chapter 7, and then the little bit we're going to do in chapter 8, to me this is the key, the bulk of what Cal 2 is about. The rest of it is just sort of catching up on other issues. But this is, to me, what it's about. You were introduced to integration. Now we've done applications and techniques. Actually, substitution is a technique in some sense. So this is just picking up them from and going from there. Now, the figure that's in your book is different from this one. I kind of like this one maybe a little bit more. The computer simulation of the Indonesian tsunami, I don't know if y'all remember, it was quite a few years ago now. Doesn't seem that long to me, but I've been around a while. It was right around Christmas, December 26, 2004. I forgot what year it was. There was an earthquake that was happened somewhere off the coast of Indonesia, and it created this Indonesian tsunami that both went toward Indonesia and did a lot of damage there, but also crossed the Indian Ocean and did quite a bit of damage on the east coast of India as well. This is the west coast of Indonesia, the east coast of, it was an earthquake, fairly deep, I think earthquake, really did tons of damage. And it wiped out lots of if you think about the coast are where most people live. If you think about the U.S., East Coast, West Coast. In the middle, there's some large cities, but a lot of them are on coasts, like Great Lakes, you know, the Gulf Coast. So people tend to live near the coast, and this wiped out whole villages and towns and lots of portions of cities. And this is a computer simulation of the Indonesian tsunami 8 minutes after the earthquake. It was created using models of wave motion on advanced calculus, and here's who did it. If that's the kind of thing you're interested in, it's pretty good stuff, okay? So let's move on from there to the real part. All right. Before we get here, let me say this. I don't know what kind of integration you'll be doing in your career and your further studies and other things like this, but a lot of times that thing that's inside the integral, we call it the integrand, there's times it looks impossible, okay? We've been doing things that were pretty easy to do, okay? Those are the exception, not the rule, okay? A lot of times this thing in here is not going to be particularly easy to deal with. Okay, so what we're going to do now for a while, especially this first part, but for the next couple parts as well, we're going to look at techniques that sometimes take something that looks impossible to do on its own, and using these techniques to get them to something that's not impossible to do. And one of these is integration by parts. Now, where does this come from? Okay. It goes back to, I bet you it's going to be everybody's favorite, the product rule. Does everybody remember that, of differentiation? If you had derivative of a product, you want to name two functions for me, or you want me to make up names? Huh? Okay. U times V. Does anyone remember how that goes? And you can call this d by dx, and this is u of x, and this is v of x. Okay? The derivative of a product of two functions. Say again? V. Say again? Okay. V times u prime, is that what you said? Okay, V times u prime plus u times v prime. You got it. Okay? That's it exactly. Now, written a slightly different way would be, I'm going to reverse the order of it, u dv plus v du. That's written sort of in differential form, okay, where this dv dx and du dx, okay. But yeah, that's the basic brunt of this, okay. Now, what if you knew one of these forms, okay, but didn't know, okay, let me back off a minute. If you were to take an integral of both sides of this equation here, the integral of a derivative is just simply u times v, u of x times v of x. And this would then be, actually you're doing integral of both of them, the integral of u dv dx plus the integral of v du dx. Okay, and this would be a dx here and a dx there. Okay, now so if you had a product, you could do that. Most of the time that's not what you're given. You're given something like this and then asked to integrate it, and you don't know how to integrate this. What you could do, you see you can integrate this part. If this is easier to integrate, subtract that from both sides, Okay? And that might be how you do it. So that's what it's leading to. If this expression here, which is generally not going to be integrable, I don't see a way, no one can see a way to do that. But if you can break this into a product, this part you can integrate. This one you can take a derivative of, and this one you can integrate. Then here's what you do. You write this one down, write that one down, take a derivative of this one, integrate that one. And that gives you a u and a v, a d, v, and a du. Take the product of these two, u times v, minus u prime v dx. Now, if this is something you can integrate, you've changed from something you couldn't to something with two steps. Yeah, that one, if you could integrate that, that's going to be fairly easy to write down. And if this is something you can integrate, go for it. Okay? You couldn't do this one. This is pretty straightforward. If you can integrate that, do it. Now, we'll run into other circumstances where you do this and that's still not integrable. But it didn't get any worse. Okay? That's what we're looking for. Even if it didn't get great, as long as it didn't get any worse, you might try it again. And then again, until you either get something you can integrate or you get something close to what you had before. So that's the principle of integration by parts. If you can split an integrand into something that's differentiable and something that's integrable. And usually when you take a derivative, it doesn't get any worse. A lot of time when you integrate, it does get worse. You jump up powers and stuff. But if you can find functions that don't get any worse, then try it. See if it simplifies things. Okay? So let's do one. Okay? Let me clear this. All right. Evaluate this. The integral of x cosine x dx. And by the way, your book, and I'm glad to see it, they wrote this integration by parts formula a lot more simply. So I'm going to write it here. U dv is equal to u v minus the integral of v du. That to me is a lot simpler, and all those x's in there weren't doing anything but just taking up space almost. So that's the same. Those are equivalent expressions. That second one is just a lot simpler. All right. Now here's what we try to do. We try to find a u and a dv. Okay? Now, again, the rule here. You want your u to be something that when you take the derivative it gets simpler, and you want the dv that when you integrate that it doesn't get any worse. Okay? Is that all right? It may even get simpler. So looking at, and there's obviously two parts of this. There's this and this, and one of them's going to have the d part's going to have the dx with it. So we can put the dx out here with the dv because you know it's got to be there. Okay. Now, which of these, when you differentiate, get easier, but when you integrate, don't get any worse? Certainly taking a derivative of x is going to be simpler. It's just going to be 1. When you integrate cosine x, what do you get? A negative sign. That's no worse than a cosine, right? It hasn't gotten anything. So I think that's the way to go. Let the u be just your x, and the dv be cosine x dx. Right? All right? Then, What do we do with the u? You want a du. Now what do you think that would be then? Du is equal to what? 1 what? 1 dx, right? We're writing as differentials now. On this side, we're going to do an antiderivative. Now, time out just a moment here. We're not going to mess around with plus c's until the end. So don't worry about them yet. So if you did integrate this, or take an antiderivative of that, what would you get? Just be a v, right? Take the antiderivative of that, and we already said it, what would that be? Negative sine x. And that doesn't, the dx was, the d's are with the d's, and the no d's have no d's. Okay, so we got it. Yes? You're right, it is a positive, sorry. I've been listening to somebody else. Okay, I wasn't thinking. You're right, it is a sine. Because derivative of sine is cosine. You're right. Okay. Now, what does your expression tell you? If you have this set up, then you can rewrite this as, leave off the integral now, u times v minus the integral of v du. Okay? Well, your uv here is, your u is x, and your v is sine x minus the integral of sine x dx. You got it. I think we can do that one, can't we? So this again is going to be x sine x antiderivative of sine x. Okay, so that's going to be a plus cosine x. And now we put our plus c, because that is an indefinite integral at the beginning. Don't do them in between. Wait till the end and put it in. All right. See how the book did? X sine x plus cosine x plus some constant c. Perfect. Make sense? And again, that was pretty straightforward. Not too bad. Okay? Let's do another one. I think it's probably just about as easy. Can I erase it? Everybody got it? Okay? Let's do this one. Integrate x e to the x dx. Now first, is there any substitution or anything else that might work there? I sure can't think of any. And when all else fails, it is a product. So let's see, what would you try? Let u equal which one? X, and dv equal e to the x dx. And I hope y'all see why we chose it that way, right? Because then, what? du is equal to dx, and v is equal to e to the x. Got it. Okay? So what would that give us our answer as being? Say again? Okay, first the uv, which would be x e to the x, right? Minus the bottom line, the integral of e to the x dx. Okay? I think even I can do that one. okay? That would be x dx, x e to the x minus e to the x. I love e to the x. And then you need a plus c. Okay. And in some weird applications or something, you might actually want to express that constant as e to the c. Okay? Because if you did that, then you could, I don't think that would be helpful. But yeah, sometimes you then might be able to combine the e's together and get you a ce to the something, but not in this case. We'll leave it like that. See how they did? Boy. They took a long time to get somewhere on this one. Oh, there it is. X e to the x minus e to the x plus c. Good for them. Now, what the rest of their stuff was doing was what happens if you got them in the wrong order. You said let your e to the x be your u and x be your x dx be your dv dx. Be the dv. Then when you integrate this, it sure doesn't get any worse. Okay, it'd be e to the x dx. But when you differentiate that, when you integrate this one, though, you would get 1/2 x squared. Okay, which now is worse than what you started with. So don't go that way. Always try to simplify the one and try to keep the other from getting any worse. Okay. All right, to clear this? Okay. All right. Let's look at example 3. We're going to try to integrate x squared cosine x dx. Where would you begin? Say that again. Okay, let the u equal x squared. That makes the dv, it's supposed to be a dv, equal to cosine x dx. Keep the d somewhere there. Okay. D's with d's. Okay. Then du is equal to 2x dx and is what? Sine x. Yeah, that's correct. Sine x. Then this would be equal to x squared sine x minus the integral. Okay, there's a 2 here and an x sine x dx. Okay, the 2 from here, the x from here, the sine x from there, and the dx. Okay, but guess what? I can't do that second integral. Can you? Unless we... Oh, yeah, so let's do that one by parts. Okay? So let's just fiddle with this one now. Then, now, I guess a pure mathematician would not like to use the same u for a different thing in the same problem. Okay? But as long as you keep them separate, I like you fine. No, never mind. Okay. All right. If you want to go to new variables, you could. Okay. But let u equal what? X and dv equal sine x dx. Then du is equal to dx, and v is equal to what? Negative cosine x, negative cosine x. One of these days that will come through. Okay, because you got dx. Okay, so this last part. Now, let's not forget our first part. X squared sine x minus 2 times, just this integral would be what? Negative x cosine x minus integral of, and you have another minus, so that makes a plus here, cosine x dx. Okay? So this will be x squared sine x plus 2x cosine x. Goodness, my pen is slowed down like crazy. Okay, and what can we do with that last one? You still got a minus 2 times that integral. What's the antiderivative of cosine x dx? Okay, sine x. Okay, and then you'd need a plus c. All right. I don't think there's much you can do to help that. I think that's about as simple as you can write it. So let's see what they got. X squared sine x plus 2x cosine x minus 2 sine x plus our good old c. Now, every example we've done so far has been an indefinite integral. That's why we had plus c's in our answers. What you reckon introducing limits of integration is going to do to us? What do they usually do to us? Second? Just give us a number? Is that what you said? Something like that, yeah. Yeah, ultimately that's what it's going to come down to. But, here's the key. You're going to have to put these limits here in this UV part as well as in the integral part. Certainly the limits are going to continue here, but you've got to evaluate this one between those limits as well. Then you integrate this between the limits, and that would require another one that you would put between the limits, and then finally evaluating that one. And then what you don't have is a plus c anymore. Okay. You may have something that's plus something out there, but it's not just an indeterminate c. Make sense? Okay. Here's how they express that concept. Well, now, number one, sorry about this. This was the last one we did, okay? I wanted you to do them, so I didn't want to get to this slide too soon, because you just reading what the slide says is not really that effective of learning. Doing it is better than seeing it done, okay? So you started out with a u dv, and once you integrated the dv, that gave you a v, so that gave you u times v. Now, if this had been a definite integral, we would have to evaluate that between those limits as well, but it's not in this case. Minus v du, and the v part was this, and the du part was 2x. So that's minus an integral 2x plus x. That becomes your new uv. That becomes the u prime v. Okay. This was up front, and then you pull the minus 2 out here and integrate that. When you go to integrate that, you have to use the integration by parts again. Okay? And keep going until it's over. And let's see. Now, here is when you have a definite integral. Same deal, except now you have limits on the integral, definite integral. You break it up into u dv, okay, and that becomes a u times v when you figure out what, integrate this, you get a v in it. U times v, but this you have to evaluate between a and b as well. Even though you didn't feel like you did an integration on it, you still evaluate it there. And then minus, in this interval, carries the same limits as before, du v du, u prime v of x dx. Okay? And then you proceed with that and whatever it takes to do that. Okay? So there's the only difference, or one of the differences. You evaluate both the product part and the integral part at those same limits. And then when you finally do that integration, you evaluate the result of that between the same two limits. Okay? So, let's on this slide do example 4. Now, I wish they had done this a little differently here, but we're going to do it. They're throwing a new wrinkle in at the same time they're doing the definite integral. I wish they had done it in 2 different pieces. Do one fairly simple and then do it, but let's go. The integral from 1 to 3 of log x dx. Now, can any of you happen to be able to integrate log x? I can take a derivative of it, and that's a very good thing to be able to do, but I can't integrate it. Okay? If you think back, when you're taking derivatives of power functions, remember, it's the x raised to some power, numerical power here. Taking a derivative of that, it's that power. You move that, make it the coefficient, the variable, and reduce that by 1. Right? Well, that worked really fine until you had an x to the minus 1 here. And when you did a minus 1, no, that's not the right way. No, I'm sorry, integrating. Okay. Well, I don't like those scenarios where you have to dream up the answer. Let's just say, when you look at that, I can't integrate it. I don't know how to integrate log x. So, does it look like that could be a product? Almost doesn't seem like there's enough there, does there? But there are 2 pieces, right? And one piece you can, as you said, integrate it, and the other piece you can differentiate it, can't you? Say that again? No, wait. Let u be, now it's got to be one of these 2 things, either this or that. Yeah, it can't be dx. That has to be the dv part, remember? The d's stay together.
Okay. So, yes, we have to integrate elements, yeah.
Right, and you told me you could do that, so I took your word for it. All right, okay. All right, so then du is equal to 1 over x dx, and over here, What's that? X, that's it. All right. Now, if this is going to work, what would this be?
That's going to be 1 over X.
No. You do UV.
Oh, UV.
Right.
It's going to be ln x, x on.
I like to write it that way. You could say ln XX, but then,
It looks wrong.
oh, that looks strange. So x ln x, that's a lot better.
Minus the
Except you got to put the limits here, 1 to 3, minus, and what were you going to say?
minus the integral from 1 to 3
The integral from 1 to 3,
of 1 over x.
yeah, x over x, which is 1.
1.
Okay, dx. Hey, now, could it come out any easier than that? Okay. Now, time out for just a second here. Could this have been 0 to 3 there?
No, it's undefined at 0, isn't it?
Yeah, log x is undefined at 0. Could that be negative 1 to negative 3 there? Or negative 3 to negative 1 there? It's everything 0 and less. Yeah, log x is not defined at 0 and not defined at any negative number at all. So these are legitimate limits because you can't evaluate it at both. Okay? Just checking. Okay? So let's do our evaluation since you said you could. Between those limits. Start with the x part. 3 log 3 minus log y1, 1 log 1, right? Anyone remember what log 1 is? 0, so that was a waste of ink, wasn't it? Minus, can you do that integral? X evaluated from 1 to 3. So this will be 3 log 3. What? Minus 3 plus 1, which would be 3 log 3 minus 2. Done. And you can plug in your calculator to see about what value log 3 is and multiply it out if you want to. But the answer is 3 log 3 minus 2. Make sense? So sometimes don't fight it. Go with the flow. I mean, there's nothing much you can do with that except, now, the thing is my rule got a little distorted here because when you take a derivative of this, I don't see that being a lot simpler, but it's not terrible. When you integrate that, that actually gets worse, okay? So that's not how we normally do, but because this product gets better, even though that got worse, the product got better, yeah, you had no other way to go. This had to be your U, that had to be the dV, because the D's have the D's with them. So you had no choice but that. Try it, see if it works. And it did. And we're happy. Or ecstatic, which are we? I don't know. All right. You want another wrinkle? And this, I can't really say why they do this. Seems like to me this should have been done back when we were doing indefinite integrals because it's an indefinite integral, but they're choosing to do it now. Goodness gracious. Got some conjunctivitis over the weekend, so every now and then my eye either itches like crazy or it just hurts, and right now it's hurting, but let's keep going. The integral of e to the x cosine x dx. Whoa. Dx. Now, any of you do that integral without Any other tricks or techniques? I think not. Okay. So it is a product, so we might want to investigate. The question is, how do you want to go? Do what? E of X. You know, that's perfectly fine. Okay? Even though E of X is a great thing to have as your dv too, guess what? Both of these can go either way. They don't get any worse when you integrate or differentiate. So, yeah, let's go for it. Let u equal e to the x. Then, and, what's the next part? dv is equal to cosine x dx. Be sure you have the d with the d. Okay? Then, du is equal to e to the x dx, and sine x. All right. So this will then be, uv would be e to the x sine x. No limits on it, so we're going to leave that alone. Minus the integral from the bottom line here, e to the x sine x dx. And guess what? I can't do that one either. So what might we try? Do it again, Sam. Okay. So I'm going to leave that part over there and put a minus here. Oh, wait. I don't want to put that there yet. We've got to do our fiddling first. Do you mind using the same letters? You okay with using these still? Okay. Let u equal. Definitely do it the same. I was going to wonder if anyone was going to ask. Okay? And here's why. If now you decide to swap them and do it, you're going to wind up right back where you started. Okay? Going nowhere. So be sure when you have multiple stages here, stick with what you started. Okay? So that would be let u equal e to the x and dv is equal to, dv is equal to sine x dx. Then du is equal to e to the x dx, and v is equal to negative cosine x done. Okay? So let's carry on from what we had before. We had an e to the x sine x. What's that? Is the first part supposed to be negative? Okay. What do you mean? U prime v down. Wait. Oh yeah, there's a minus out in front of all that. Is that what you're asking? Yeah. So I was just going to write it down, okay? But then what's your first part of that? Times the negative cosine, so that's going to make that one a plus e to the x cosine x. Now you had a minus already, and now you got another minus because of the subtraction of the integral, so that's a plus. And what goes inside that? The bottom line here, e to the x And you got the minus again, cosine x dx, so then it changes that plus back to a minus again. That's what I say. You have to watch these sign changes, okay? And do we have a problem here, Houston? What? Okay, it keeps repeating. But maybe it's not too big a problem. That little thing here, you can just bring down here, right? So let me do that. Integral of e to the x cosine x dx is equal to this. And guess what? This is the same as that, so add this to both sides. I swear, such a pain in the neck. Okay, so what do we have here now? 2 times the integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x. And guess what? All you have to do is divide by 2. And there's your answer. This integral, what you're starting to begin with, is equal to that. So sometimes repeating reduces one enough so you can finally do an integral at the end. But other times repeating, it may take a couple of steps, it may take more than a couple of steps, but at some point, if you ever get back to the same thing you had before, plus or minus a constant somewhere there, then move it back to the other side and let the constant go with the other. Now, they phrased it as 1/2 e to the x times cosine x plus sine x. They factored out the e to the x. Oh, I forgot the plus c. At the end, always remember the plus c. So they factored out e to the x in the 1/2. So that would be e to the x over 2, and then what they had left was sine x plus cosine x. But for some reason, they wrote cosine x first and sine x second. They're just adding. Adding is commutative, so it doesn't really matter. If my pen would write, there it comes. Okay. They say cosine x plus sine x. I said sine x plus cosine x. Perfectly fine. But you do need the c there because it wasn't in there. Okay. Does that make sense? Okay. Integration by parts can accomplish a fair amount. Okay. Now, sometimes you can get into one of these loops, and basically all you can do is get another form. And especially if it's a sort of an indeterminate number to begin with, like an n there, then what you get is a form that you call a reduction formula, but the other name for it is recursive formula. Both of those names work. And that's what, excuse me, goodness gracious, that's what we're going to hit next. Okay, before we do, here is their rendition of what we just did. Let's see how they did it. Okay, they started out by identifying this as your u v prime, which then would give you a u prime v, where v being sine x. And guess what they did? They let e to the x dx be the v prime and cosine be the u. Oh no, can you do it that way? Why not? Of course you can. But that then gave you your integral of d du. Okay? With the minus minus here. I don't know why they brought the minus in here. I would put the minus here. But the VEU, the V being the e to the x, and the DU being the sine x. Okay, only that's the minus. Okay, so that's where the minus sign. Boy, did they, doing it this way, especially the way they wrote it, skipping steps, is really hard to keep up with your minus signs here. I'm hoping they did it right. I think they did. Okay. And then they do it again, but again, because they let the e to the x dx be the v prime and the cosine be the u, then they've got to do the same thing here. The second time, and this is just that second integral they had there, and that's the, so they let this be your dv, and that your u, and that vu dv, uv, and then minus v, which is the e to the x, du, which would be your cosine x dx. Okay. My eye hurts. And again, I wish they weren't skipping steps and not showing how they did it, but they did. And that winds up being exactly what we started with before. So you wound up with two of those, and you would have that term in front and that term at the second. So the first was the e to the x cosine. So that's why they did a cosine plus sine. I did sine plus cosine. So it doesn't really matter which one you choose. If both of them are going to get no worse when you integrate and no worse when you differentiate, then it doesn't matter which order you do. All right. Now they're recursive. Okay. Also called reduction formula. Well, we saw this basically back when we did eyes hurting, I'm sorry. Example 3, when we had x squared cosine x dx, we had to do 2 steps before we could get it done. Now we have x to the n with something that can be your dv here. It could have been a trig function, it could have been a sine or cosine function, it could have been e to the function, whatever you have here. But you see, since this is not known how many that is, all you can do is indicate what happens in the first step. Okay? And let's just do it. What would you say? Let u equal x to the n, and du, dv is equal to e to the x dx. Okay? Because you see that doesn't get any worse when you integrate it. The other improves a little bit when you differentiate. Then du is equal to n x n minus 1, and v is equal to e to the x. All right. Then what would you have? Yeah, let me write down what we're trying to do. Integral of x to the n e to the x dx. The other thing about conjunctivitis, it makes brightness really a pain. Literally a pain. Okay, this is what we're trying to get, and what do we do from here? x to the n, right? E to the x, that's your uv, minus the integral of, I'm going to put the n out front. Oh, I left off the dx here, sorry. Always need a d with a d, okay? Bottom line, x to the n minus 1, okay, e to the x dx, okay. Don't forget the whole bottom line, okay? Now, guess what? We don't know what n is. We don't know how many times we do it. But what did we do? We reduce that power of n by 1. So that's why they call it a reduction formula, okay? And the other name was recursive formula. It just keeps repeating itself and as long as you need it to, okay? So I'm sorry, I wasn't paying attention. The slideshow has e to the x there. Your text has sine n to the x. Sorry about that. Let's do that one as well. So I'm going to go on and okay. Yuck. I don't want to end this. It's such a pain in the neck. There's going to be 2 slideshows here. Sorry about that. We'll just pick up from current slide and go back to it. This pain in, wait a minute. Yeah. This is what we'll do. The one they did in the book, I wasn't paying attention, is this one. The integral of sine n x dx. Okay. They're telling you to derive the reduction formula. Okay, without really telling you how to do it. So let's take a look and see what we need to do on this. This is a lot more esoteric than the other was. Now, last time we had one that was sort of like this, what did we do? Second? Yeah, we've been doing by parts. And what were the parts? Parts are parts, right? Which one do we do?
Made sine the trig function to the
Okay. Okay, say that one more time. Let
u equals
sine to the nth. Is that what you said? Okay, and dv equal dx. Okay. Now the problem with that is going to be that dv becomes an x. I mean, the v becomes an x then. Okay. And the last time we did it, it was a log x here, and the derivative of log x was 1 over x, so that didn't get any worse because of the product. However, this doesn't have that characteristic that allows you to do this. So here's the trick. Okay? And it is a trick. Okay? Let's not quite do this yet. What we're going to do here is rewrite this as the integral of sine to the n minus 1 x times sine x times dx. You might say, why? Well, the other didn't work very well, that's why. So let's do it like this. Now, we have a function here that we can start stepping down, right, by taking derivatives, okay? And this one, by integrating, it's not going to get any worse. So let's see what happens with that. See, before, we're just using a dx, that's going to get worse. It's going to be x at the end, which, when you integrate that, it's not going to be any better. So now let u equal sine to the n minus 1 of x, and your dv is equal to dx, okay? Then du is equal to n minus 1 n minus 2. Got a chain rule problem, don't we? When you take the derivative of a composite function, which is a power function and a trig function, you have to then take the derivative of the innermost function as well. It's n minus 2x, and you then have a cosine x. Derivative of sine would be cosine x. Now you've got your dx, okay? Let's do the other side of this one, and what does that give you? V is equal to negative cosine x, that's just negative cosine x. Okay. Now, what does this give you? What does that give you? Okay. I'm going to go and pull the minus out too. Minus sine n minus 1 x cosine x. Okay. Minus, and that other minus is going to make it a plus when you do the bottom line here. The integral of, and let's pull out the n minus 1. That's not doing anything to help us in there. And this will be sine to the n minus 1 minus 2 of x cosine squared x, because you have a cosine here and a cosine there. The minus already went out front for you, and then you have your dx from here. Okay. Now, what does this indicate? If you integrate that, it sort of indicates that you drop the sign by 1, and you have a cosine there, plus a 1 n minus 2, that is, I think it is. No, n minus 1. N minus 1 sine to the n minus 2. Boy, that's ugly, isn't it? My minus ran into my 2, and it's just really ugly. Let me clean up this a little bit. Okay, and this a whole lot. Maybe even that a little bit. Okay. That was a minus and a minus, meaning a plus n minus 1, not a lot better, cosine to the n minus 2. That's what that was supposed to be, x, cosine x dx. Okay. Now, that's just one step, and for the life of me, I don't see quite. We've done everything they did. That step comes up fine. Then we have got it. The problem child in this, goodness, how did that get so ugly? Oh, I erased the C and forgot to put it back. Okay, there we go. Okay, I thought my X and C ran together. Okay. The thing that's messing this up is that cosine squared, but if you remember, that's the same as 1 minus sine squared x, right? Okay, so let's rewrite that answer then as minus sine to the n minus 1 x cosine x plus 1 over, no, plus 1, plus n minus 1. I'm trying to get that. Okay, and that'll be the integral of sine to the n minus 2 x minus sine to the n x dx. Okay, now what has happened there is this thing is that now. So the first part of that is just this. And the second part of this is this times that, minus this times that. Well, sine to the n minus 2 times sine squared is going to be sine to the n again, which is what we started with. So let me rewrite this again. The integral of sine n x dx, okay, is equal to, let's go to the very end here, minus the sine to the n minus 1 of x cosine x plus n minus 1 times the integral of sine of the n minus 2 x. Okay, pause a moment here. Minus the integral of sine to the nth x dx. This has a dx here too. Yuck. Okay. Now, this n minus 1 goes in front of that one too. So when you subtract, I better do it. Okay. Integral of sine n x dx is equal to minus sine n minus 1 x cosine x plus 1, n minus 1 times the integral of sine to the n minus 2 x dx minus n minus 1 times the integral of sine n x dx. Okay. Now let's add this to both sides. Okay. And that's equal to minus sine n minus 1 x cosine x plus n minus 1 times the integral of sine n minus 2 x dx. Okay. These go out because I add to 0, and this gives you a 1. I don't know why I keep wanting to do that. Okay. I do know, but yeah, it's just 1. Okay. It's 1 plus, these are the same, so it's 1 plus this. Well, 1 plus this would be 1 plus n minus 1. So that would just be n. So that gives you an n here times the integral of sine nth x dx is equal to this mess, okay? And then divide out the n, so it would be minus 1 over n, the sine to the n minus 1 x cosine x. It's a minus. It doesn't look like a minus. Okay. Plus, and this will be a n minus 1 over n, that same one when you divide it by n there, the integral of sine n minus 2 x dx. Okay. So this is the recursive formula. This thing here is equal 1 over n times this, that's a minus that, times that, plus n minus 1 over n times that integral there. So we haven't solved that yet, but we have reduced the power by 2. You have this out front, and then you have that. And then you keep doing it either until this goes to 1 or 0. If n's an odd number, it's ultimately going to go to 1. If it's an even number, it's going to go to 0. And when it goes to 0, you can stop because you've already gotten the answer. That would just be 1. So that's the formula they get. And let's see if we got the same thing. Negative 1 over n sine to the n minus 1 of x cosine x plus n minus 1 over n times the integral of sine n minus 2x dx. Yeah, got the same thing. Now, it then says, as if that wasn't enough, evaluate the integral of sine cubed. So what I'm going to do here, because I do not want to keep this much on the page, so I'm going to change that to a cube here, and I'm going to erase all this mess, stuff, or junk, or whatever you want to call it, and just save my answer. Okay. Wow, all this writing, and goodness, that stings my eye like crazy. It would have almost been better just to erase it all and just write down those parts again. But was afraid I wouldn't write them right, and then I'd be trying to figure out what I did wrong. Okay, stop here. Now, in the old package I had, it was a package called Tegrity, not this Screencast-O-Matic, which is really cheap, literally and figuratively. I could have just circled that and take it to the top. This doesn't allow me. They called it lassoing it and taking it to the top. I can't do that now. So either I got to write it up there or just leave it separated like this. So this is going to be sine cubed. Using this formula here, our n is equal to 3, right? From what we had before. So this is going to be negative 1/3 sine 3 minus 1 would be 2 sine squared x cosine x plus 2/3, right? N is 3. N minus 1 would be 2/3 times the integral of sine, and 3 minus 2 is 1, so that to be sine x dx. Does everybody follow what we did? We're using this formula down here, but with n equal 3. It'll be a minus 1/3 sine 3 minus 1 is 2 sine squared x cosine x plus n minus 1 is 3 minus 1 is 2 over 3. The integral of sine x dx. Well, I think we can do that one, can't we? So this is minus 1/3 sine squared x cosine x plus 2/3. What's the antiderivative of sine x? Negative cosine x. Okay? All right. So this will be minus 1/3 sine squared x cosine x minus 2/3. I'm sorry, cosine x. Right. Now, I think no reason to try to simplify that, but they probably do. Let's see if they do. Negative 1/3 sine squared x cosine x minus 2/3 cosine x, of course, plus c. Okay. So we did get that. Now, in exercise 58, which I'm not going to assign because it's even, but you'll be asked, would have been asked to derive this, and it looks almost the same. The integral of cosine nth x dx is going to be 1 over n, just like you had here, only it's the positive 1 over n, not the negative we had here. Cosine to the n minus 1 x sine x plus, same as below, n minus 1 over n integral cosine n minus 2 x dx. Okay. So you see the difference between this one when you had an n in it, and sine and cosine. Difference is for sine a minus, for cosine plus, 1 over n, same function, sine for this one, cosine for this one, to the n minus 1 times the opposite function, sine, cosine here, and then this part is the same sign, n minus 1 over n integral cosine n minus 2 rather than sine n minus 2. So there are two recursive formulas that you will later see at the back of the book, in the table of integrals and so on. All right, want to do preliminary questions? Why not? Which derivative rule is used to derive the integration by parts formula? Product rule. Very good. Number 2. For each of the following integrals, state whether substitution or integration by parts should be used. Let me just make sure. Yep. Okay. Let me erase what I got here. Anyone need this any longer? Okay. That was really exciting there at the end, wasn't it? I mean, edge of the seat type material. Okay, so which of the following integrals, for each of the following integrals, state whether substitution or integration by parts should be used. Okay, here's the first one. The integral of x cosine of x squared dx. Okay, substitution or integration by parts. You choose. Second? That's the substitution. Okay, very good. Second one of these. The integral of x cosine x dx. Parts, okay? Parts is parts, okay? We'll just leave it like that since she said it that way. How about this one? Integral of x squared e to the x dx. That's parts as well. Okay, let's do the fourth one down here. Integral of x e to the x squared dx. That's the substitution. Okay, very good. Let's make sure they got it right in the back. They tend to miss things really frequently, don't they? I'm just kidding. Okay, I tend to miss things pretty frequently. Okay. Integration by parts is from the product rule, and they don't do number 2 in the back. Sometimes they do the odds, and sometimes they do them all. They didn't do that. So let's do number 3. Okay, here's our integral. Integral of x cosine x dx. Okay, and they say, what about this? Let u equal cosine x dv equal x dx. Good choice or not? Why not? So what?
U should be X.
Yes, u should be x because you're going to take a derivative of this, which doesn't get any worse, admittedly, but when you integrate that, it does get worse, and with no hope of getting better. So if you move this over here and this over there, then differentiating x gets better, and integrating cosine x still doesn't get any worse. Okay, it is a poor choice, and that's why. Now let's see how they worded it in the back. They do have this answer, which is pretty obvious. Transforming blah blah increases the power of x, and yeah, makes a new integral harder than the original. Okay, same thing. Homework exercises here. Goodness, my eye. Any of the odds 1 through 5, and then you have a whole bunch of them here. Any of the odds 7 through 33, and I would do some of the easier ones, some of the little more esoteric ones. Okay, do number 35. It's the only one they have like that. Then do any of the odds 37 to 45, and any of the odds 47 to 55. Okay, then do any of the odds 57 through 65. Now there's a variety of problems there, so do some of whatever it takes so you can feel pretty confident you have the understanding. Then do any of the odds 67 to 73, and then any of the odds of the rest of those 75 to 85. They have further insights and challenges that you certainly can use if you want to. I always look for them to see if there might be a potential paper topic buried somewhere there. I don't see any there. So any questions on 7.1? Making pretty good progress today. Pretty exciting, isn't it? Of course it is, yes, okay. All right, sucks, I hit the wrong key again. All right. Now that has a couple of breaks in PowerPoint, but here's just another one. Okay, moving on to 7.2. As you see, Chapter 7 is a long chapter, so I'm glad these are fairly short, direct sections. I'm growing hungry and thirsty because I didn't get to eat, but maybe a little over half my salad. So I'm running out of steam pretty quickly here. Wait a minute. Where in the world did that... Back up one more time. 7.2. Okay. Wait. I think the organization here between the two texts is pretty big, okay? And here we see, whether you realize it or not, the last thing we did in 7.1 is the first thing in the old 7.2. Without much preamble or anything else, it goes straight to this. This is what we derived at the end of 7.1. That the recursion or reduction formula for sine to the n x dx is minus 1 over n sine to the n minus 1x cosine x plus n minus 1 over n integral of sine n minus 2. So you see you reduce, you have this one term here that has this stuff in it, but then you reduce the power that you integrate by 2. And you can keep doing this, and as I said before, when you get down to, if n is an odd number, then you keep reducing by 2 till you get to sine to n equal, n minus whatever is equal to 1, then you just do the integral. If n is an even number, then you get down to where that would be integral of dx. You have other stuff in front of you. And the cosine n formula that we just derived or talked about at the end was the sign changes here from minus 1 over n to 1 over n. But then the sign changes to cosine n minus 1. X sine, the cosine changes to sine x, plus n plus 1, n minus 1 over n times cosine n minus 2. Okay. So that was done at the end of the currents of the previous section, 7.1 in the new edition. It was done at the first of these trig formulas, trigonometric identities here. Okay? Now, okay. Trying to piece together how to present this. That's the first slide that we've already done. Okay. sort of ignore this. This is the old text. Okay? We're going to do something somewhat similar, but not quite the same. Where we move from in the new edition is here. Okay? We could do that very problem based on the things we just had, but in the new edition, here's what we do next. The integral of sine to the m x cosine to the nth x dx. That's what we're going to go for now. Okay? Now, here's our approach. If either of these m or n, these are your powers of your sine and your cosine, if either of these is odd, zoom in on that one. Zoom in on the odd number. If both are even, we're going to have to come back and do that later. Okay? But if either of those is odd, now if one's odd and one's even, doesn't matter which one you choose. But the easiest case is when at least one of those is odd. Okay? Now, the first one we're going to do is exactly the last one we did before. Okay? So I don't know why they're repeating it, except just to remind you. Okay? Except they're going to show you a different way to do it. Okay? I guess that's fair. So here's an odd power of sine, the integral of sine cubed x dx. Now, go back a couple of slides. You're going to see us that we've already done this. But I'm going to show you another way to do it. Okay? No better, no worse. Actually, probably a little bit easier than the other one. What we're going to do, anytime that either the m or the n are odd, whichever one is the odd, here's what you do with it. And this one has cosine. The n is 0 here, so you don't see that one at all. Okay? First thing you're going to do is split this into the integral of sine squared x times the sine x dx. Now, would everybody agree that's the same as sine cubed? Yeah, of course. Okay. Now, next step. What is sine squared? 1 minus cosine squared times sine x dx. Right? Now, would you buy this? That's the same as the integral of sine x dx minus the integral of cosine squared x sine x dx. Buy that one? What I did was distribute this 1 times sine x to sine x minus cosine x sine x dx. Right? Split it into two integrals. Okay? I think even I can do the first one. Right? What would that give you? Negative cosine x. Done. Right? How about the next one? Minus. What could you do with that? Substitution, I like it. What would you substitute? That u equal, a little louder, bless you. Huh? I don't think so. All right, good choice. Okay, cosine x. Why? You take the innermost part of the most complicated part of it. Cosine squared is more complicated than sine squared. Innermost function is cosine. Let that be your u. Then what? du is equal to negative sine x dx, right? Oh, and look what we've got. Here's the minus, so that becomes a plus, and the cosine becomes a u, and the du is your sine x dx, with the minus sign already taken care of. So this actually becomes plus the integral of u squared du, isn't it? Okay, I think we can probably do that one, can't we? Minus cosine x plus antiderivative of u squared du, u cubed over 3. Okay, I'll go on and put the plus c here so I won't forget it later. So this will be minus cosine x, and what was the u again? Cosine, so this will be plus cosine cubed x over 3 plus c. Okay. So they, goodness gracious, my eye hurts. They wrote the cosine cubed first, cosine cubed x over 3 minus cosine x plus c. Now, let's flip back just one piece of paper and see what they did for sine cubed x before, and this doesn't look anywhere close, does it? Until you realize that their answer before had sines and cosines in it. If you merely substitute, okay, here's the answer we got before. We had the integral of, this is on page 376 if I can read, sine cubed x dx, and we got the answer then to be negative 1 over 3 sine squared x cosine x minus 2 over 3 cosine x plus c, right? Now, what I'm going to do is take this sine squared x, just like we did before, change that to 1 minus cosine squared x. Would you allow that? Okay. So that would be a minus 1/3 cosine x, and the 1/3 times 1 times cosine x, plus 1/3 times, is minus times minus, 1/3 times cosine squared x times cosine x, so that would be 1/3 cosine cubed x. Okay, and then we have a plus 2/3 cosine x plus c. Well, I'll buy that these two are the same. Oh, this is a minus, sorry about that. Minus, so those two add to be a minus 1. So that would be minus cosine x. Yep, that's the same. And frankly, this form's a little bit easier to me. I mean, it has only cosines. You don't have the cross terms. You don't have as many fractions. You know, yeah, I like that a little bit better. Okay, but this one's still true from our recursive formula for sine, but doing it this way makes it a little bit easier answer, perhaps. Okay. I think what I do is erase all this. Goodness gracious, my eyes, this thing. This one does. So evaluate this one. The integral of sine fourth x cosine fifth x. What you reckon we're going to do with that? Okay.
Unrelated, but you wanted us to let you know when there was like 5 minutes left.
Oh. Okay. We're almost there. We're not quite. I got 1:31. So yeah, we're almost there. So I'm glad you stopped me. Let's see. By the time I go make the copies, yeah, that may be it. It may be a good place to stop for next time. Okay. So let's say we'll start with example 2 next time. Okay, that one that I got written there. And homework exercises here. I think you can do any of the odds 1 through 5 just based on what we've done so far here. You can try 7 if you want to. And we'll pick up the rest of those later. Okay, so let me run down. Goodness gracious. So what I think I'll do is end the recording now. I'm going to pause the recording now. I think you'll recognize that 1 and 2 are from, what was it, 5, 6, or whatever that section we did on substitution. 3 and 4 was, I think it was 6-1, which dealt with area under grass. 5 and I think 6 are both from 6-2. And 7 and 8 I think are from 6-3. 9 is from 6-4, and 10 is from 6-5. I believe is how those broke down. So you probably would have figured that out on your own, but if that was helpful, so be it. All right, good deal. Sorry that we went a little over, not too much. And